Hi, I'm Yogesh Surendranath. I'm an assistant professor in the Department of Chemistry at MIT, and my group focuses on how to manipulate the reactivity of interfaces at a molecular level to try to use electricity to selectively rearrange chemical bonds. And we try to do that through an array of tools in the hopes that one day we'll be able to make technologies that'll be able to use electrons as tools for storing electricity, using them as tools for chemical synthesis, and really transforming our energy landscape in a way that chemistry and electricity are really one and the same. So one of the things that really motivated me in my program is kind of asking what are the central questions that relate to enabling new energy storage technologies? And if you think about what electrical storage really means, it's you're taking electrons and you're storing them in some sort of chemical bond. It could be the ions that flow through a battery, or the chemical bonds that you make or break in a fuel cell or an electrolyzer, or the charges you put into a redox flow battery. But what it really involves is this conversion between electrons and the chemical energy that you store it in. And so we really want to think about what are the fundamental processes that make that efficient, make that selective, make that robust and long-lived. And that's really the core of what unites our research program, and what we've come to the realization of, and this is not just us, it's really many members of the community, is that the rubber meets the road at the interface between an electrode and solution. That's literally where the electrons hop from your current, whether it be the wires that come out of a solar farm or the grid power that you simply take out of the socket. It is that place where the electrons jump from their electrode to solution or some material to be able to do the reaction that actually stores that energy in chemical bonds or chemical redox changes. And so what we try to understand is what is the fundamental chemistry that mediates the selectivity and the reactivity of that interfacial boundary, that boundary between solid and liquid or solid and gas, where the electrons actually make the leap from the circuit to the chemistry. And that's really what our group is all about. And that has manifestations for really every sort of energy conversion technology that we're thinking about today, and all the ones that will be there in the future. And when I got started in this, the thing that really inspired me was this realization that for really one of the first times in humanity's existence, we're going to have, because of the build-out in solar, the build-out in renewables, a time when electrical energy is actually going to be, at certain times of the day, more plentiful, more inexpensive than the energy that we dig out of the chemical bonds we pull out of the ground. So let me just kind of rephrase that and talk about it for a moment. If you think about how society has operated in terms of our energy landscape for the last literally several hundred years, since the dawn of the Industrial Revolution, we basically dig chemicals out of the ground and we burn them and we use that to make electricity. And now for the first time we have the possibility of actually reversing that cycle, where we take electricity from the sun or from the wind or from geothermal or from nuclear, some other non-fossil fuel source, and actually turn that into energy that we use as chemicals, whether it be commodity chemicals we use in materials, or it be chemicals that we use to store, or it be simply ways that we store that electricity to be used when the sun doesn't shine, or at night, or at a time when there's a cloud around. So those are the kinds of things we try to focus on. And to us, it's really the chemistry that occurs when you take an electron, you move it into solution, and use it to make or break or rearrange chemical bonds.